Okay, so welcome back after the break. And today it's a pleasure to have Peter Sarnak from IAS in Princeton and Princeton University. And as I explained, his talk, is related. So we have two talks in a row about the joint collaborations with physicists between. And so today is more the mathematical side, and next week we'll have the physics side. And the title is about prescribing the spectra of cubic graphs. As I said, also we have two microphones, so don't hesitate to ask for the microphone if you want to ask a question. And the floor is yours, Peter.
Okay, thank you very much. It's a pleasure to give a talk here, even if it's on a Zoom at Collège de France. So I think this fits well in the series of lectures that Nalini has advertised, so hopefully it'll be clear how it does. So let me start with the context of which of this lecture. So the main setting is that we have a locally uniform geometry. So locally the geometry is constant curvature, constant Riemann curvature if it were Riemannian geometry. So it fits into Cartan's classification of symmetric spaces in that case. But we're going to look at some very specific examples. I'm just giving you the context. And we have an invariant differential operator on this local geometry. So the local geometry will be a quotient of a globally uniform geometry divided by a deck group of motions, which preserve the geometry. And the quotient is assumed to be compact, but I'm going to always assume that I'm trying to understand how the spectra of some invariant differential operator looks as these quotients have bigger and bigger volume. So the quotients will always have discrete spectrum because they're compact. And in our setting, we're going to have graphs. So it'll be completely linear algebra, everything, nothing fancier than linear algebra to set it up. And the big question that we want to ask is, what gaps can you create in the spectrum? And I'll explain why this is of interest in a second. So in many ways, this is a problem that's been studied from many different angles, and people ask, can you hear the shape of a drum and things like that, inverse spectral problems. The inverse spectral problem of saying, well, what numbers are the spectrum of something is, in any generality, is basically impossible. But the question we'll ask is a kind of a stable version of that when the volume, the sizes of these locally uniform geometries get large. So local uniform geometries are, the simplest types are Euclidean space. And the questions I would ask in that setting about Euclidean space would be ones that quickly become related to the geometry of numbers. That's, I'm still setting up the context here. But perhaps the most interesting setting for me, maybe for Nalini as well, at least in her earlier works, are hyperbolic quotients. So your constant curvature, constant curvature spaces like hyperbolic surfaces. Hyperbolic three manifolds are very interesting, and the problems that we ask in that context are very, very interesting, and there are some interesting developments in recent times. And the discrete analog of all this would be a local uniform geometry, which would be a Brouillard-Tietz building. And I have to mention Tietz here since he's was in the Collège de France. And those, the operators that commute will be just, everything would be linear algebra. The quotients of finite local buildings. But that's the context, and everything I said there you can forget about, because I'm going to be talking about the absolutely simplest case of this, which is the case of a locally uniform graph, which is a regular graph. And I'm going to even stick to regular of degree 3. That is, each vertex has 3 edges coming out of it, and it's a finite graph. So that, we call this, I think combinatorics call this cubic graphs, and I'll stick to that terminology. Why I'm sticking to 3 regular, there are places in which the proofs of some of these theorems will depend on that fact that it's 3 and not 17 regular. Most not so, but some things will. And the practical problem of prescribing the curvature the spectrum, which, as I should have said myself at the beginning, this is all joint work with Alicia, Kollar, who you'll hear from next week, and also Fan Wei, who's a combinatorist. I'll explain which the works, the attributions a bit later. But Alicia Kollar is a physicist, an applied physicist, and she actually builds various waveguides, and these problems come up naturally there. And in her laboratory where she builds these, they can only make cubic layouts. So she certainly wanted to fixate first on three regular graphs. All right, so cubic will denote the set of all three regular connected finite graphs. The smallest of all of these, I hope you can see this cursor here. The smallest of all these is just the smallest three regular graph. I don't allow loops and I don't allow multiple edges, is K4, which is just the complete graph on four vertices. There's an eigenvalue. We'll return to that in a minute. And then the next smallest is a bipartite graph, K33. So this bipartite means that the vertices can be broken into two sets of equal size and all the edges run between the two sets. These are the two smallest, and actually they'll also be extremal for the spectrum. And then you increase the size of the graphs, they grow quickly, and we want to prove theorems about large three regular graphs or make statements about them. You quickly hit this famous Peterson graph on 10 vertices, which is, as if you open any elementary book, they'll say is a counterexample to every naive conjecture, including some of the things that we talk about here. All right, so that's the setting. Cubic denotes that. And if you have a cubic graph that can be realized in the plane, it's a planar cubic graph, then it can be realized in such a way, topologically, in only one such way. That's a theorem of Tutt. And we'll be using the subset of planar graphs to demonstrate rigidity features of this prescribing of the curvature, prescribing of the spectrum. I don't know why I got this curvature in my brain. Okay, so let's look at the universal cover of any of three regular graph is the three regular tree. Actually, in this work, it's not just the universal cover that's going to play a role. Again, we can look at all intermediate covers in order to engineer gaps in the spectrum, but the universal cover, as the word universal suggests, is of course the most important. Okay, I'll denote by the number of vertices of the graph by n. N will be going to infinity always. And the spectrum that we're interested in is either Laplace spectrum. When you're in a uniform geometry, these operators are simple polynomial expressions, one in terms of the other. So I'll use the adjacency operator rather than the Laplacian, which is the following operator. We better understand what it is, because all the theorems are about this the spectrum of this adjacency operator. So firstly, we look at the vector space of functions on the vertices, complex or real valued, and we define the operator AF. So on such a function, the adjacency operator on F is you sum all y's joined to x by an edge. The graph's symmetric, of course. Not of course, it's an assumption. I'm assuming my graphs are graphs. So AF is sum of y joined to x of f of y. And that takes me from functions on the vertices to functions on the vertices, and it's a linear operator. And it's symmetric in the basis, the obvious basis that you choose with delta masses at the vertices. So we have a symmetric matrix, finite dimensional, n dimensional. So it's got n eigenvalues, and the spectrum is real. And it's very easy. I'll leave it as an exercise to show that the spectrum lies between -3 and 3. So all the eigenvalues are between -3 and 3. And since I've assumed that the graph is connected, it's also an easy exercise to see that 3 is a simple eigenvalue, and the only other eigenvalue that has an immediate meaning is -3, which is an eigenvalue with simple if and only if x is bipartite. And the rest of the eigenvalues, so the biggest one is 3, and it's simple. So the next one, lambda 1, that's going to be an important eigenvalue. And another important one is the smallest one, lambda min, lambda n minus 1. You might ask why I name this lambda naught, not lambda 1. I think from hyperbolic geometry and eigenvalues there, I've got into this habit and I stick to this habit. Now, there's one thing I'm going to use later, which has not been used much in this context, even in graph theory. And it'll be absolutely critical in understanding some of the things. And that is that the eigenvalues are, if you write down the characteristic polynomial of this matrix, if you write down the standard basis, you'll have a matrix which has got zeros and ones. It's a matrix of zeros and ones, three ones in each row and column, and symmetric. That's what our graph is. That's what our adjacency matrix is. And so the characteristic polynomial will be a polynomial equation with leading coefficient lambda to the n leading coefficient 1. So the eigenvalues are going to be algebraic integers. But they're going to have a much more important property, is that every conjugate, so every other eigenvalue, because if I take Galois conjugate of the equation, will also be an eigenvalue, and it'll be so these eigenvalues are totally real algebraic integers, and I'm going to use that crucially later. All right. One other thing we need to know before we can start to ask and answer questions is the spectrum of the adjacency operator or matrix on the full infinite three-regular tree. This is not a trivial problem, and I emphasize here L2 of T3, meaning the Hilbert space of square summable functions from the vertices to the complex numbers. So the minute you put L2 on a tree, on something which is growing exponentially, meaning the volume of a ball radius r in a tree, so the number of vertices whose distance r from a given vertex, it's homogeneous, grows exponentially. So to be in the L2 spectrum, to be close to being square integral, the eigenfunction, if you had an eigenfunction, would have to decay exponentially. And that's a very crucial point, and it leads to the spectrum of the L2 spectrum of the adjacency operator A on the tree. Not, of course, it's contained still in -3, but it's actually smaller. It's contained in -2√2, this magic number, +2√2. And just for your, just so that you see it with your eyes, 2√2 is less than 3. It's about 2.8284, and so on. So the spectrum is absolutely continuous. It's contained in a shorter interval, and that'll play a very big role. The first person to, I think this was done simultaneously and in entirely different subjects. Kind of interesting. So this was computed by Keston. It's a famous computation of Keston of the spectrum of a random walk on a tree on L2 of this. So I repeat the L2 aspect. It's also the two-adic Plancherel measure computed by Sally and Shalaika for PGL2QP, where QP is 2. So PGL2QP divided by its maximal compact, just like very much like the SL2R divided by its maximal compact is the up-off plane. PGL2QP divided by its maximal compact is a P+1 regular tree. So if P is 2, it's a 3 regular tree. And the Plancherel measure is central to representation theory of this non-compact group and was computed by Sally and Shalaika first, I believe. Okay, so the number 2√2 is extremely important. And the question of the title of this lecture, and be used in the next lecture of Alicia, is what gaps can you create for these three regular graphs as x gets large? And to motivate it, I myself been working on this maybe since the 1985 or so. The gap at the top, that is the difference between lambda 1 and 3, or 3 minus lambda 1, which, well, I'll call here the base note gap. Base note, if you were thinking of the Laplacian and then you were thinking of it as a drum, so to speak, this would be the base note, lambda 1. That gap is a very important gap in combinatorics. It is the very defining quantity for what's known as an expander graph, which have proved to be very useful in combinatorics and computer science and in engineering as well. So that's a gap that we've been familiar with. Maybe if you haven't heard what an expander is, I highly recommend the article by Vigdis and Huri and Lineal called Expanders in the Bulletin of the American Math Society maybe 15 years ago. And it explains how powerful and useful these expanders are. So the very definition of an expander, a definition of an expander, is that it is a sequence of three regular graphs like this, that they are very sparse because they're three regular, and yet they're highly connected because this gap measures some connectivity in terms of all sorts of quantities. And I'm not going to spend too much more time on that because the features I want to explain is there are other gaps that are of great interest, and that's what I'm highlighting in this lecture. So actually, Alicia, who came to talk, ask questions about this is how we started to collaborate, found that in work she was doing in tight binding models, Hamiltonians in certain settings, which I'll show you a picture of in a second, it was the gap in three regular graphs at the bottom, at -3, that was more important. And in chemistry, in old-fashioned chemistry, and also in the theory of fullerenes and carbon clusters, three regular graphs, if you've taken a chemistry course, you always, three regular graphs are all over in the pictures there. And the the spectrum, that's the gap that's important, is the gap in the middle. So the gap sort of which divides the top eigenvalues from the bottom eigenvalues. This was first introduced by Huckel in orbital stability, but in any event, it's played a big role. I don't know how important it is decisively at this point in chemistry, but mathematically, it's a fantastic question. So once you see this, you must ask yourself, well, there's the gap at the top, there's the gap at the bottom, there's a gap in the middle. What gaps can we create? That's the question I want to answer. And this can be asked for any uniform geometry and should be asked for any uniform geometry. And we understand a few things, but much of it still remains open. So I think Alicia will explain to you quantum surface codes use of these, which are more recent. But earlier on, she has a paper in Nature with collaborators where they make these waveguides. They build them in a laboratory. They look like this. They're three regular layouts. They need to understand in this tight binding model the spectrum at the bottom. Can you make a gap? And they want to make hyperbolic waveguides, and they're discrete, so they face these kind of three regular layouts that you're seeing. This particular thing is actually something they build. I'll leave that to her, and I will stick to the math. Okay, so now I want to tell you what we know. So the base node spectrum is something that captures the gap at the top. So base node will always mean the gap between 3 and the next to biggest eigenvalue. I will return to the more general the other gaps in a minute. But since this is by far the most studied, it's been studied in the theory of expanders for years and years, I want to tell you what we know. And so this theorem here, which has a lot of dots, is due to many, many people. And I will summarize it very quickly in the next slide. But let me first explain what this definition is. So look, cubic was always 3 regular finite graphs. F is a subset of cubic. It may be all of them. That'll be the first example. And then the planar subset is very important, especially in applications, what you can make with planar graphs. And I'll define the following, which measures how can you prescribe lambda 1? What can you create for lambda 1 as you go over larger and larger graphs? So the base node spectrum for the adjacency of the subset F, which you should just think of 2 subsets right now, either the full set or the cubic or the planar subset, is the closure of the base node eigenvalue. So lambda 1, remember, is the next to biggest eigenvalue below 3. I go over all the possible values I can arrange for lambda 1. There's only countably many graphs, finitely many with any given n, 3 regular graphs. And I'm going to go over all of them, and I take the closure of that set. That set will tell me what possible lambda 1s you can prescribe. So this is a subset between -1 and 3. I should have said back in this first slide. So the next to biggest eigenvalue for K4 for the complete graph. So the 3 is the biggest eigenvalue. Turns out that the complete graph, the next to the biggest eigenvalue, is very, very far from 3. So this gap is very large. It's easily seen to be the largest gap you could create. It's -1 with multiplicity 3. Of course, this has got a symmetry, so it's got high, should have multiplicity. It does. So then the top eigenvalue is 3, and then the next 3 eigenvalues are -1 with multiplicity 3. So that's the biggest gap, and K33 has got lambda 1 equal to 0. It's the next to biggest gap. And if you increase the size of the graphs, you might think that lambda 1 will increase in the same way. No, it's very tricky to keep lambda 1, to try keep it away from 3. That's the expanded question. Very difficult, but very well understood today. So we're going to take the closure of that set. So the closure of the set, as you go over all cubic graphs, which the -1 is the smallest that you could ever have for lambda 1. And then what is this subset that you can create? And it's a closed subset of this intervals. So it's going to have a discrete part and a limit point part. And here's what we know. We know completely the answer to this. And as I said, I'm not going to give attributions because it's a combination of many, many people's works. So firstly, the answer for cubic, so this is I call it the base node spectrum because it's the spectrum of lambda 1s. So if we go over all cubic graphs, lambda 1 can be -1, it can be 0. I've pointed this out. The next it could be is 1 with multiplicity 4. You can find 4 such graphs. And then you can find graphs, and you can find infinitely many, and this is already rather deep. You can find infinitely many which all have a gap which is quite big. They all have lambda 1 less than 2√2, strictly less. So the discrete part is infinite. That's something that you might call a super Ramanujan graph, because a Ramanujan graph is one which has this biggest gap here, that lambda 1 is less than 2√2. That's the definition of a Ramanujan graph. And these are super Ramanujan in that it's actually less than 2√2s. That little extra twist is something that I appreciate anyway. Okay, and then you can make lambda 1 dense inside 2√2 and 3. So the base node spectrum has a very beautiful description. It's discrete here. The existence of these infinitely many, as I said, is quite non-trivial. The fact that it has to I'll explain the attributions in the next slide. So the discrete part is this infinite set in -1 open 2√2, and then you can accumulate the continuous part of that base node spectrum is 2√2, 3. So it's got a beautiful description. I'm very interested in the rigidification. So if you are trying to prescribe and then you put conditions on the graph, so you may say, well, what can I do with planar graphs rather than arbitrary cubic graphs? Then all of a sudden things rigidify completely. That is, the base node spectrum of planar consists of a completely discrete set. So it also obviously is contained in -1 because K4, the complete graph, is planar. So the -1 is an eigenvalue. And then the eigenvalues, lambda 1, will have to march up to 3. It can't stay anywhere below. So the only limit point is 3, and the spectrum became rigid. So you can't make a gap at the top. You can only make a gap with non-planar. So I hope that's clear, that this answers what the prescription of lambda 1 is completely. And let me just run through how these things are proved. So for planar graphs, the fact that lambda 1 must go up to 3 is actually, I'm sure, known to people, not maybe first by computer scientists, but it's a well-known theorem of Lipton and Tarjan about separations of planar graphs. That is, that they basically compute what's called the Chaire constant. They wouldn't call it that, but the Chaire constant is related to lambda 1. So you can tell whether lambda 1 goes to 3 by trying to divide the graph into 2 pieces which are roughly equal size, and at the boundary, the edges going between the 2 pieces is much smaller in number than the size of each. So it's a separator theorem. And if you're planar, you can always find a separator. And they do so very explicitly. And that immediately makes lambda 1 go to 3 as the size goes to infinity. So that's the simple proof of this last part. Planar is rigid. Quite simple in this situation. The fact that this with three regular graphs, you can't keep it, you'll have to accumulate at least 2 root 2. You can't make the lambda 1 less than 2 root 2. That was first proved by Alon and Bopana. It's a well-known Alon-Bopana theorem showing that the optimal gap that you can make with three regular graphs is this gap 3 minus 2 root 2. There's a very explicit version of it due to Joel Friedman. Joel Friedman has made some very important contributions here. I know Nalini is very interested in developing his works in the context of hyperbolic setting and Weil-Peterson geometry. But here he has two decisive theorems. Well, this theorem, part B here, is just the best we know about this. He's got the world record on this. So the fact that the spectrum's discrete up to 2 root 2, that's Alon Bopana, but he actually gives you an estimate that lambda 1, in terms of the size of x, must be at least 2 root 2 minus 100 over log x squared. All proofs lead easily to log x, but he's got a log x squared, which is slightly bigger. And I don't know any better than that. I don't know what the truth is there, actually. The fact that there are graphs which keep lambda 1 less than 2 root 2 or less than or equal to 2 root 2 is the fact that they exist Ramanujan graphs. These were first constructed using number theory by Lubotsky, Phillips, and myself, and separately by Margulis. But so the existence maybe is a bit surprising. And I, for many years, was always saying the only way you're going to make these graphs is using number theory, because the input we had to prove the existence of these was to use Weis-Riemann hypothesis for curves over finite fields at a crucial input in these explicitly constructed graphs. It turns out that if you want to make these super Ramanujan graphs so that lambda 1 is actually less than 2 root 2, you have to go a little bit further than what Weil has. And you have to go into the proof of Weis' proof of the Riemann hypothesis to make sure that an eigenvalue doesn't occur to zero of the zeta function doesn't occur at a specific point with a multiplicity. And a graduate student here of mine, Nina Zubrelina, has used work of Coleman and Eidixhoven to construct infinitely many arithmetic number theoretic graphs which have lambda 1 strictly less than 2 root 2. Not by much, exponentially close, I'm afraid. And it uses a fact that in the proof of the Riemann hypothesis for curves over finite fields, which is the input that allows to put all the eigenvalues in this range that we so much desire, Weil gave two proofs of this. You can read it in his autobiography. It was when he was running away in the Second World War. He found two proofs. One was an ingenious elementary proof, and the second used Jacobians of curves. And in that proof, he actually proved that Frobenius, whose eigenvalues we're talking about, is semi-simple, a thing that we only know in the case of curves. So the more general case that Deligne solved of the Weil conjectures, we don't know the semi-simplicity. It's a major unsolved problem. Anyway, that semi-simplicity is enough to get you these super Ramanujan graphs. I would say this was all very beautiful, except there's another construction, and so we're not, yeah. Oh, coming back here. Yeah, this, super D is a discrete part, yeah. Yeah, sorry. No. Okay, it's because I put together two different lectures. My apologies. I cut and paste. Yeah, it should be super D. Yeah, and sub is here all adjacency only. Yeah, thank you. Yeah, so the okay. So to describe the set of lambda ones, I think is not possible in easy terms. It's like you're saying to me, what is the set of all numbers which are lambda ones of large matrices which have 3 zeros in each row and column and symmetric? I don't think that is an easy description. If there were, anyway, it's a countable set, and I'm saying that if you take the closure, we get a very clean answer. We get a discrete part and a continuous part. It's, I think, very natural. Okay, when you define spectrum of an operator, you have the point spectrum and the discrete and continuous. But this is it's a good question. You might, in some of these problems, you might actually ask, what is the set of lambda ones themselves? Sorry. Gee. You can see it, right? Your screen has been forward. Yeah. Resume share. Okay, I'm back. Okay, thanks. Sorry, my computer did something weird there. All right, let me get back to this description. So there, as I was saying years ago, I believed certainly that the only way you'll ever make Ramanujan graphs is using number theory. But there's this remarkable work, maybe 8 years ago, maybe more, 10 already, by Marcus Spielman and Srivastava, who gave a construction of Ramanujan graphs by using the input that's similar to Weil, or the Riemann hypothesis, is a Li-Yang theorem from statistical physics in the form of Hellman-Lieb, which gives that certain constructions of certain matching polynomials have their eigenvalues or their zeros on a circle, very much like the Riemann hypothesis for curves. And then a very ingenious interlacing argument to show that you can always choose double covers and the new eigenvalues you get will be in the location you want them. So there's a purely, computer scientists were not happy with all this arithmetic constructions, even though the arithmetic constructions that we have are much richer and very useful. They managed eventually to find this ingenious proof of the existence of Ramanujan graphs. And in fact, their proof gives super Ramanujan, meaning ones for which lambda 1 is strictly less than 2 root 2, by something better, 1 over the cardinality rather than exponential in the cardinality. So they beat us at that. All right, so I'm just going over explaining that there are infinitely many of these guys. And there are 2 proofs of that. And then the final part is only very recent. So the final part was that you can make lambda 1 dense here. It's a countable set, but you can accumulate at any point that you would want to. And that is a lovely recent theorem of Fanway and Norga-Alon. And it uses, I'll just say roughly how it's proved, is you use the fact that if you take a random 3 regular graph, it's not Ramanujan, but it's almost Ramanujan. This is this theorem of Friedman that I alluded to a minute earlier when I was on this page. That is that if you take it at random, you don't know that lambda 1 is less than or equal to 2 root 2, but it's less than or equal to 2 root 2 plus any epsilon for any epsilon you choose to begin with probability going to 1. And there's a much stronger version of that due to H.T. Yao and his collaborators. And when they prove this theorem that the random graph is almost Ramanujan, they actually show that the eigenvectors are all delocalized with high probability, something that we don't know in the arithmetic situation, but which is very interesting on its own ground. Anyway, in the random case, they show you almost Ramanujan and you delocalized. And the fact that the eigenvectors are delocalized allows, so this is where Fan and Noga start, allows them to start with such a thing and then to make a few little moves which don't change the eigenvalues except the one you want to make near any limit point, which is bigger than 2 root 2 and between 2 root 2 and 3. So they posted their paper recently and you can find the proof. I just say, I'm pointing out that the starting point is this theorem of Friedman that I mentioned, and that Nalini has been investigating in the hyperbolic setting, where this proof of Friedman is very complicated. There are other proofs that have been found since of this almost Ramanujan, but understanding it properly, especially as it might apply in other situations, is very important. Okay, so that was the gap. And I've spent too much time on the well-known gap, which is the expander gap and the extremal expander gap called a Ramanujan graph. Let me say a few words about the gap at the bottom, which is what, as I said, Alicia brought up to me in the first place. So here there's a very beautiful story. So at the bottom, suppose I have any connected graph Z, doesn't have to be regular, even finite. The line graph of Z is the graph formed by taking the vertices, the edges of the original graph and making them vertices, and then connecting two edges if they have a vertex to the new vertices of the edges, and the new vertices are connected if they have an old vertex in common. So that's called the line graph. And it's like a dual object to the original graph. And the spectrum of the line graph, the adjacency matrix of the line graph, this is why I'm using adjacency rather than Laplacians, because it's got this nice feature. The adjacency matrix of the line graph, its spectrum, the line graph's a new graph, and you can ask about its adjacency matrix spectrum. It's related to the adjacency matrix spectrum of the original graph, because there is a matrix called the incident matrix. This is all, you can find this in Biggs's beautiful book called Algebraic Graph Theory. If you take the matrix formed out of the edges, I'll say there are m edges and n vertices, and you make a not square matrix, but a rectangular matrix with m by n, size m by n, and then you take that times its transpose one way, and that times its transpose another way. One way you'll get the spectrum, the adjacency matrix spectrum of the graph, and the other way you'll get it of the line graph. And of course, the spectrum of A transpose A and A transpose in the other order are related by linear algebra. And that leads to the following, that the spectrum, the adjacency matrix spectrum of the line graph always has an eigenvalue -2 to the multiplicity of m minus n. If m is bigger than n, you'll have, and if m is much bigger than n, like it will be in our situations when we set this up. So there'll be an eigenvalue -2 with high multiplicity, and then the rest of the spectrum. So this is coming from the kernel and the co-kernel in this A transpose A and A transpose the other way around. And then you get the spectrum of -2i, the adjacency matrix of A, and then plus the diagonal matrix, which has got the degree of each vertex. I'm not assuming things are regular here. This is a very general statement. But what you learn from this is easily seen to be positive, AZ plus DZ. So the spectrum of the line graph of any graph, the adjacency spectrum, is always contained in -2 infinity. So remember, I'm trying to understand the bottom of the spectrum, and this is saying that if you have the line graph of any body, the smallest eigenvalue is always, the line graph will create, by taking a line graph, you can always make graphs which have their spectrum start at -2. And I'll call the person who first made great use of this was Hoffman. So I'll say a graph's a Hoffman graph if the smallest eigenvalue is greater than, this is of the adjacency matrix, and the graph doesn't have to be regular, if the minimum eigenvalue is greater or equal to -2. And there's a characterization of these incredibly. So any line graph is a Hoffman graph. And the characterization, remarkably, is basically you have to be a line graph or some generalized line graph or something called a cocktail graph if you're going to have this property that the smallest eigenvalue for the adjacency matrix is -2. And the reason is the following. The smallest eigenvalue, just from the variational principle, is things are symmetric, so it's the minimum of this Rayleigh quotient that we're all familiar with. And so if you have a subgraph, so suppose B is an induced subgraph of our starting graph Z, and I write down this quadratic form, and when I'm on a subgraph, I can just take the variables to be 0 and restrict to the subgraphs, which amounts to looking at induced subgraphs B of Z. And from this variational characterization, you immediately see that lambda min Z is less than or equal to lambda min B for any B induced subgraph of your starting graph Z. So if you are a Hoffman graph, then you can't contain any small b's, and you can go look for any small b's, as induced subgraphs which have lambda min actually bigger than -2. A Hoffman graph is a graph, any graph, finite graph, for which the minimum eigenvalue is bigger than or equal to -2. Yeah, the adjacency of it, yes. Okay. And I'm saying that that's very hard to have I'm going to give you a theorem now. It's not mine. No, so here it is. So because a Hoffman graph cannot have induced minors of certain types, there's a very, the works of Seymour and Robinson show that when you have these graph minor, if certain graph minors are not allowed, there's often a classification of what you're looking at. This is a Seymour-Robinson theorem. It's not that effective, but in this case, there's a fantastic classification due to Cameron, Goethals, Seidel, Schult from 1975 that these Hoffman graphs, they classify what these Hoffman graphs are. They have to be line graphs. So every line graph is a Hoffman graph. They have to be line graphs, or they are subsets of root systems, Cartan-type root systems, especially in E8, and a sporadic subset of a finite set of sporadic graphs can also be Hoffman graphs without being one of these specific line graphs or cocktail graphs. So there's an amazing theorem in this paper called Line Graphs, Root Systems, and Elliptic Geometry, where they classify Hoffman graphs. And we're going to use this in order to discuss gaps. Oh, I'm going way too slowly, sorry. So here's a way of making graphs, three regular graphs, which are going to have an optimal gap at the bottom. We've discussed the gap at the top, and the gap at the bottom is actually easier once you have this amazing classification. So I'm going to define a map from cubic graphs to cubic graphs. So cubic were all three regular graphs, finite, connected, and simple. And I do it as follows. I start with any cubic graph, finite cubic graph. I take the midpoints. I take the subdivisions. I just take the midpoints of the edges, and at the midpoint, I put new vertices. So I put a bunch of new vertices. And now I get a 2-3 regular graph. And then I take the line graph of that. And that will, you can check, will give me a 3 regular cubic graph again. All that the operation did was it took every vertex in my original 3 regular graph and it sews in a triangle there in an obvious way. So I'll have 3 times the number of vertices. So that's a way to think about it. But because this operation, I land up as a line graph, it turns out that the image, that if I start with any graph and then apply t to it, the new graph's a line graph, so the smallest eigenvalue has to be greater than or equal to -2. So it's a way of constructing graphs which have a big gap at minus. These graphs obviously can't be bipartite, because remember, if you bipartite, you have -3 as an eigenvalue. But what this does is allows me to immediately construct many graphs just through this map T, which have their smallest eigenvalue bigger than or equal to -2. In fact, equal to -2, because the line graph has an eigenvalue -2 with high multiplicity here. And using that classification of theirs, we show in a paper here with Alicia, Kollar, and her co-authors, who are the co-authors on that Nature paper of theirs, that any cubic graph, which is a Hoffman graph, so has its smallest eigenvalue greater or equal to -2, is either K4, which we've already seen is got smallest eigenvalue -1, or it's a line graph and is in fact, if it's large, it's in the image of this map T. So it has to be of the form T of some smaller graph. So we in this way can understand completely what the gap at the bottom is. So the gap at the bottom, so the gap at the top was these Ramanujan graphs. The gaps at the bottom, the only way the biggest gap you can ever create is, you can't keep unless you're the K4, but if you're large, then the biggest gap you can make at the bottom is to keep all the eigenvalues greater than or equal to -2. And you can do that, and the only way you can do that is by making line graphs through this construction, by this sewing in operation T. Since I'm going very slowly and I want to explain the big rigidity theorems, I'm going to skip this further discussion of the bottom, and I'm going to immediately move to the main definition. So once you see the bottom and the top, and I'm going to also discuss the middle, it's very natural to ask what subsets of can be gapped. What gaps can you create, period, by making large graphs? So a subset of cubic, I'll always allow myself to restrict to subsets. So I'll say an open subset of -3,3 is a gap set for this subset curly F. If there's an infinite, the key word here is infinite sequence of graphs, which are in F, which have no eigenvalues in U. So that U is a gap set. So we've already seen some gap sets like this. The complement, I'll just call a spectral set because sometimes it's easier to state the theorems in terms of this complement. So a closed set is a F spectral if there are infinitely many elements in F, all of whose eigenvalues are contained in K. So I want to make big gap sets and small spectral sets. And a very important practical problem, one of the key problems we're able to solve is, given a point in 0, 3, can I find a neighborhood of that point which is a gap set? So can I gap every point in 0, 3, or maybe, and if I restrict to F, at what point do I lose the ability to gap? So I hope these definitions are completely natural at this point. So -3, -2, that's a misprint. Should be -3, -2 is a maximal cubic gap set. These are the Hoffman graphs. 2√2,3 is a maximal gap set. That's Alon Bopana and the fact that they exist infinite sequence with no eigenvalues there. That's the existence of Ramanujan graphs. So we can ask this question for any set, and specifically, what can you gap and what gaps can you create? So we just extended the problem to more general subsets. I'll skip the algebraic geometry. All right, so I'm going to now state the big thing we understand about this. It's not a complete understanding, but I mentioned at the beginning that I'm going to use, or we find it very useful to use that the eigenvalues of a graph are algebraic integers, and all of whose conjugates are also algebraic integers. And there's a beautiful theorem of Fekete from 1930, very simple theorem in which he invented transfinite diameter in order to explain this theorem. So suppose I have a closed subset of the plane, I'll call it K, compact. The transfinite diameter of K is defined as follows. You try put down endpoints, you put down endpoints inside K, and you try to make the geometric mean of these points as big as possible. So you take the maximum of where you put the points, and this is the product of all distinct points, the I minus j, divided 2 over 2. The number of points is n choose 2. So you take that root, and that is dnk. It's very easy to see that the sequence is decreasing, and you take more and more points, and that the limit of this decreasing sequence is called the transfinite diameter of the set K. It's also called the capacity of K. There's a potential theoretic definition of this. In fact, it showed the following remarkable fact, which is quite easy from the fact that the characteristic polynomials will have integer coefficients. And it's the following, that if K is a compact subset of the plane and its capacity is less than 1, so the capacity of an interval of length R is R over 4. We can't compute the capacity of too many things. The capacity of an interval is computed using Chebyshev polynomials, for example. So if the capacity is less than 1, and suppose the set contains an infinite sequence of algebraic integers and all their conjugates, then if the capacity is less than 1, then there can't be such an infinite sequence. In other words, your set has to have a certain size, capacity at least 1, to entertain or to accommodate a infinite set of algebraic integers, meaning integers whose degree gets higher and higher, an infinite set of algebraic integers such that they are in the set and all their conjugates are in the set. So an example of a set of capacity which is 1 is the circle, because you've got roots of unity, and a conjugate of a root of unity is a root of unity, and they all lie in the circle. And I told you the interval of length length r has got capacity r over 4. So if you have an interval and you have a subset of an interval which is less than r over 4, it can't have infinitely many algebraic integers, all of whose conjugates are also in a set. All right, now our spectrum, I'll skip this. Robinson has a converse to that theorem, and there's some very interesting developments. And in fact, one of Sarah's most recent papers from maybe 3 years ago is exploiting this Robinson construction. This will be relevant to us because the eigenvalues of a three-regular graph have this property that all their conjugates are also in the set. And so it's not going to be surprising. There's going to be a constraint on the spectral sets that they have to have capacity 1 if you're going to be able to create an infinite sequence of graphs with some property. Okay, so here's the first main theorem. This is joined with Kollar from 2 years ago. And it gives a description of what kind of sets about maximal spectral gap sets for three regular graphs. So any cubic spectral set, So remember, a spectral set means a subset of 0, -3, 3, such that there's an infinite sequence of three regular graphs, all of whose spectra lie in K. If you have such a spectral set, it can't be too small. It has to have capacity at least 1. A cubic gap interval, so I'm trying to make big gap intervals. We've seen at the two edges, a cubic gap interval can never have length bigger than 2. So if you have any subinterval of -3, 3 whose length is bigger than 2, then it cannot be a gap set. There are only finitely many three regular graphs which have no eigenvalues in that set. So we're getting some insight into what these spectral sets look like. Probably the most important and useful thing for them is that every point can be gapped with planar graphs. With planar graphs, I emphasize, even with planar graphs. So again, what that means is you give me any point between -3 and 3, there's a neighborhood of that point such that there's an infinite sequence of planar graphs which have no eigenvalues in that. Now that might look like it violates the expander property, that planar graphs can't be expanders. But when you choose your point, if you choose your point very close to 3, I will make the neighborhood I'll make will be, of course, very close to the point and not close to 3. But every point can be gapped. There are planar cubic graphs whose spectral sets have capacity 1. So this is showing that the extremality of the first theorem and of the second theorem. And the interval -1, 1 and -2, 0 are maximal gap intervals. You can actually make intervals, and this interval -1, 1 is kind of nice, and it's maximal. So let me just, and you can even do it with planar graphs. So let me repeat what this says, is that if you take the interval -1, 1, there's an infinite sequence of three regular graphs, and we found them explicitly, such that they're planar and they have no eigenvalues in -1, 1. And if you make any interval bigger than -1, 1, then that's not possible. Any set bigger than -1, 1, it's not possible to do it. So this is a max. So in this prescription of the spectrum, the thing you really want to understand are what are all the maximal gap sets. And we don't know them all, but we are getting some insight. Okay, I was going to explain the proofs, and I don't want to go too much over time. In fact, I have no right to go over time at all. So I want to I'm going to skip the proof, the discussion of why each of those steps there. The fact that you can gap every point makes heavy use of this operation T, which takes three regular graphs to three regular graphs. And when you do that, you use that relation that I'd written down before between the spectrum of T of X and the spectrum of X. And then to create the gap at any point, we'll end up using rational dynamics of this quadratic map x squared minus x minus 3 in order to prescribe the spectrum suitably at any point C. So it's the tools that come to prove these things come from unexpected sources. So it's kind of nice. But what I do want to explain in the last 7 minutes is the following, which is where the joint project, which is we almost completed by Fanway, Alicia, and myself. And this was a question that practically they were very interested in when they build these waveguides. So I'm going to now restrict to planar three regular graphs. And when you planar, you can realize it in the plane topologically. I've mentioned this before in a unique way. So you can talk about, since the planar graph, you have Euler's formula, and you can talk about faces, edges in your realization of this three regular graph. So for any integer k, let fk denote the planar graphs which have at most k edges per face. This is uniquely defined. Equivalently, the duals of these are triangulations of S2 for which the degrees in the triangulation of the degrees of each vertex are at most k. So it's easy to see from Euler's formula that f of k is finite if k is less than 6. That's just immediate. So f6 is really interesting. So these are triangulations with at most degree 6, or these three regular graphs where the number of faces are at most 6 for each. The number of sides per face is at most 6. These have been studied actually by Thurston in a paper that's absolutely beautiful. He calls these triangulations of non-negative curvature, and he actually parameterizes them in terms of orbits of integer points under a linear action of an arithmetic subgroup of SU91. Of course, he didn't point out it's arithmetic. That was not quite his. He gave a discrete subgroup of SU91, which parameterizes these F6s. F7 already for k greater than or equal to 7, so that we allow 7 sides per face. They're already very rich. They grow exponentially. What Thurston wanted to show is these only grow polynomially. From this parameterization, one can actually count how many of these in closed form using some number theory, which was done by Engel and Smiley recently in quite a beautiful paper using the Ziegler-Weyl formula. But that's besides just something I love. All right, so there's something about F6, which, as I said, is special in that, and as I say, the number of these grows a little more slowly. And the question that we want to ask is, what gaps can you make for F6? And the subset of F6, so F6 is every face has at most 6 sides. The subset of F6 where every face has exactly 6 or 5 sides is called the fullerene. And it's of great interest in chemistry, and you can find a lot about it. So these are examples of fullerenes. So they are planar 3 regular graphs. By Euler's formula, you will have exactly 12 pentagons, and then the rest will be hexagons. So the shapes are going to be where you put these blue guys. So the football and so on are here. They're Ramanujan graphs, by the way. And if you're going to make some shapes, how you degenerate them, as I told you, Thurston can even parameterize these in some quite complicated way. But you're going to, in these things called nanotubes here, you're going to have 6 blue guys, pentagons here, and 6 pentagons on that side. And then you can make this thing get longer and longer. So there are many ways of degenerating these fullerenes. But these fullerenes, of course, are very special, and so it might be much harder to prescribe gaps in the spectrum, and that's the question we want to address. So here's our theorem. So firstly, we wanted to generalize the theorem that you can planar gap any point if you allow arbitrary planar graphs. So the first thing was to see if you restrict the number of sides, can you still planar gap any point in -3, 3 when you restrict to planar graphs which have at most k sides, so in the fk? And the answer is yes. And of course, the 64 is not correct, but we worked very hard to get that a finite number, yes. So putting the restriction on a bounded number of sides per face does not prevent you from making a gap in the spectrum at any point. And the argument's quite complicated because before we just had the rational dynamics of that little quadratic map. Now it becomes a little more complicated. And that is one involved thing. We expect this to hold all the way down to K down to 7. That is, we expect that 7 sides are rich enough to make gaps and to have a very rich structure in the gap set. However, 6, which is the fullerenes or subset of that, 6 is already really interesting. These Thurston case. So if you have at most 6 sides per face, then rigidity sets in a major way. The only interval that can be gapped there is any subinterval of -1, 1. So there's a unique maximal gap interval. So this is a complete description of what you can gap. The only gap set you can make are open subsets of -1, 1, period. That's the biggest. -1, 1 is a unique maximal gap interval. And for fullerenes, the answer is even more pretty. So it's going to be more restricted than F6. So we're going to be a subset of -1, 1. And the only points that can be gapped are, these are algebraic numbers coming from some polynomial equations. So there's an interval -a plus a, and a is about 0.382. It's an algebraic number, and it's certainly smaller than -1, 1. So this subinterval -a is much smaller, and you can gap any point in -a except a unique point b. So you have to remove this point b. You can't gap b. But any other point can be gapped. So that was one of our aims, was to answer the question, what is the gap set for fullerenes? And this is the complete answer. The techniques that go into the proof of this are quite interesting, because what is this point B here? So, and they sort of mimic hyperbolic geometry a lot. There's a whole construction of capping of so what you have to study things like this. So first we study these long nanotubes and understand what their spectra are. And then we have to cap them with these 6 pentagons on each side. And this leads to a one-sided cap and some bound states lying inside half nanotubes, and eventually uncovers this point B. I realize now that I've got way too much here, and I'd hoped to say something about the proofs, both of this theorem and of that theorem, but I couldn't resist forcing this theorem to be there and taking up the last 5 minutes. So let me apologize for not giving any proofs. I hope at least the results will interest you enough. And I'm going to send Nalini these lectures with references. The paper with Alicia, which this theorem is, you can read the proofs. They are published recently. But this last paper, if anybody's interested, we have a draft which we're happy to circulate. And of course, I'm happy to answer it. Yeah, so I will put references at the end. I realize this is all just 3 regular graphs. You can ask this for any of the locally geometries that I started out with, and each one is a fascinating question, many of which we've studied in one form or another. But in this arbitrary gap situation, say for hyperbolic surfaces, is completely open, really. Like, what can you make a sequence of hyperbolic surfaces with a gap not between 0 and a quarter and things like that? There's some progress, but basically we don't know the answers as complete as here. And we don't have the Facketer theorem to, of course, enjoy. All right, anyway, I think that's what I had. At least I managed to state the 2 theorems.
Thank you.